we've talked about limits before, just looking at pictures, and we're going to use those pictures to help make sense of some new theorems in section 1.3. So theorem 1.1 has 3 parts. The first part says that the limit as x approaches c of b. So let's just think about that. What would that equal? Well, first we have to understand that it says that c and b and n, well, c and b are real numbers and n is a positive number. Of course, we're not using n yet, but so c and b are just numbers. So if the function is b, it means the function is just a number, like 3 or 4 or 7. And what does a function like that look like? It looks like just a straight flat line. Okay? So at any point here or here, any of these that we would call c, what's the limit going to be? Well, the values are all the same. So no matter where we pick it, from the left and the right, it's always going to be approaching the same value, which is b. So this would be b. Okay. Number 2 starts to say the limit as x approaches c of x. Okay. So let's see. We're doing number 2 here. We're just going to use the same graph. What does this function look like? Well, it's just f of x equals x, or y equals x. Right? Whatever I put in for x, that's what I get out for y. I put in a 1, I get out a 1. I put in a 7 or so, I get out a 7 or so. And it's just that 45-degree angle line. So for this one, what's this going to equal when I take this or this or this or this or this to be c? I come along here to this c, whatever it is. I come up and I start to evaluate the limit. I'm coming in from the right and the left, and it's just going to be, since every input is exactly what you get for the output, it's just going to be whatever the input is, and the input was x. So this limit is going to be x. The third one, the limit as x approaches c of x, okay, very similar to this, except for now we're raising it to the n. Alright, x to the n. It's going to be a little different because this function here is a polynomial function. So at least over here we can just start to get a grasp of it, a sense of what's going on. It's going to be something like this. You could think it was like x squared or x cubed or x to the 5th or so on. It's going to look something like this. At least in this area it is. It might look different over here in the negative x direction. But this gives us an idea. Let's just draw an intuition about what's going on here. So if I come along here, what's going to happen? I come to some x, and in order to get the output, I do x to the n, whatever power it is. So I come to this x, I raise that x to the n, and I have my output. Okay. So what's going to be the limit there? Well, right here is just x to the n. So whatever we choose as c, whatever x we choose as c, is just going to be that c to the n. So that's what it is, c to the n. And so hopefully we've got a little bit of intuition about that theorem, 1.1. The next one, theorem 1.2. Theorem 1.2. There's properties of limits, and they kind of just make sense. Okay, so I'm going to draw an xy, and we'll start to look at it. The first one, the first part of theorem 1.2, says the limit as x approaches c, of course, of, and b makes another appearance. B is just a real number. what's this going to be? So let's gain some intuition about it. Well, say that this is f of x, this curvy thing. What's going to happen if we multiply this function by some scalar, some number, b? Well, if I multiply this function by 2, that would mean that every point on it got 2 times what it is, what it's worth, you know. Let me actually, I can just do that and try again. Okay, and we're back. So if I were to do this and I actually cross the x-axis or something, right? So say this b was a 2. So everything's going to be 2 times what it is, what it's worth right now. So here at the zeros, it's not going to get any bigger because 2 times 0 isn't any bigger, but this guy here is going to be twice as high as it was, and this one here is going to be twice as high as it was. And we can start to connect these, right? And then this is going to be 2 times. It's going to dip 2 times lower. This is going to just shoot off the charts. Something like that. You know, it's going to go way up here because these numbers get quite big. So what's happened then? I'm going to trace this this times 2 one with blue. What's happened to any limit that we want to take? Say here. Well, it used to be here. The limit for f of x was here, but all the points on this new blue graph are 2 times as high. So the limit must be 2 times as high, or b times as high. Okay? So this would just be b times whatever the limit was at f of x. You know, this is assuming that the limit as x approaches c of f of x is equal to some number, L. Okay, then all this is true. Okay, the second one, the limit as x approaches c of f of x plus g of x. We've got 2 functions added together. What are the limits going to be? And of course, this is assuming that the limit as x approaches c of g of x is also has its own value, and we'll call it k. Okay, so let me erase some stuff here and down here. Alright. So let's say this is f, and this is, get a lighter blue, this is g. But when we add 2 functions together, what happens, of course, this y value gets added to this y value, and you get this new y value. How about this? So it looks like maybe this is added to that, so we're about here. And then this is added to this, so we're somewhere in this neighborhood. This big thing is added to this big thing, so it would be quite far up here. So, you know, it looks like we're going to have something like this is going to be what happens when we add f, this green one is f, and g. The y values are just going to get added together. Well, let's say that this is c. Here's the limit for f at c. Here's the limit for g at c. It's this right in here, this y value. And so the new y value is going to be whatever the limit was for f plus the limit for g is going to be this guy way up here. Okay, so it would just be L plus k. Whatever the limit was for f plus the limit for k, it's going to be the new limit for f plus, or whatever the limit was for g, f plus g. We're going to have this new limit up here, L plus k. 3. It's the same deal except for Okay, so kind of a similar situation. If we have a function f and a function g, we're not adding them together this time, we're multiplying them. So it's going to be somewhat similar to this. It's just going to be much higher because we've got these numbers that we're multiplying together. And whatever the limit was for f and whatever the limit was for g at c, we're going to multiply those two limits together, and that's going to be our new limit way up here, past this place somewhere, way up there. So we just have a situation where it's L times K. Okay, and I'm not going to ask you to hang in there while I go into depth about all of these because they're all pretty much the same. Right? It's going to be, if we take f and we divide it by g, now everything that was a y value of f is getting divided by the y value of g, and so we must have L over k as long as k doesn't equal 0, because we have 0 in the denominator. So that little caveat added to that one. And the limit as x approaches c of f of x, but not just f of x, we're going to raise it to some power n, some positive power. Well, here's f. If we were to raise all of these y values to the power of n, then say this were the y value of the function f right here were 1. Let's say that's 1. And then I were to raise, okay, let's say it's 2. Then I was to raise 2 to the, what would n be? Maybe 3. So you take 2 to the third, that's going to take it to 8, and there you go, that's your new limit. So that would just be whatever the limit was. In this case it was 2, and we're going to raise it to the n power. Okay, so hopefully if you've hung in there, you've gained some intuition. Intuition is if you can look at something that you've learned and you can kind of make a connection with it and it just sort of makes sense to you, that's a good place to be. Alright, so theorem 1.3 says that if you have this function p, right, or p of x if you like to call it that, it's a polynomial function, which we should know what that is. Some examples are x squared, x to the third, x to the fifth, plus 3x to the fourth, minus 2x to the third, plus 5. Anything that's like this, where we have a bunch of x's and they're all raised to some different powers and they've got some coefficients and stuff. These are all polynomials. So it's saying that if you have some function p, then the limit of this function as x approaches c, since all these functions are these nice curvy things, they're all over the place. But if you want to know about the limits, remember, say this is c, and I want to find the limit as x approaches c. Well, that means put in some values to the right and to the left, and see, are they approaching one single value? Well, for a polynomial function, sure they are. They're approaching this value. And what is this value? It's just the value of the function at c. If I were to take c, plug it into, say, this function, say this were the graph of this function, then, which it couldn't be, but let's pretend. Let's put this one up here. So now it's possible. Anyway, if I were to take the c and plug it into the function, then I would get this y value right here. And that would be the limit. And it would be that easy. And that's what it's saying. Just take c, put it into your polynomial function, and that will be your limit. That's what we call direct substitution when we do limits. Okay? So if you got a polynomial function, you can just do direct substitution. And what they're saying here is, on this next one, right, this was 1, and the second part is the limit as x approaches c of r of x. Now this r of x is this function, p of x over q of x. And p and q are just polynomial functions. And as long as q, well, we'll go to that in just a second. So here is r of x. R of x is rational function. That's why it's r. It's a rational function. It's a polynomial divided by a polynomial. So it's just two polynomials, which is kind of like a new polynomial function in a sense, with a few caveats, but pretty much that. So if it's just pretty much a new polynomial function, we can just say, well, it's just going to be plug c into the rational function, and there you go. That's going to be the limit. But the only thing is that at that point, c, q of c cannot be equal to 0, right? So to get a picture of this, let's call this one p. Let's just use that as p. And let's use this one as q. Okay? Now, if we were to come right over here, and we were to say this is c, well, I could take this value, or you know what, that was absolutely wrong. Let's come right here. This is c, not at their intersection, but right here. So we've got this limit for p is right here. This limit for q is right here. If I were to take p and divide it by q, I'd be taking something dividing it by 0. Right? So at the point c, q is worth 0. And so this wouldn't work, right? If we were to do the polynomial function, there would actually be a vertical asymptote right there if we were to draw it out, because that's where the function q is worth 0, and you'd be dividing by 0. Okay. What this is really setting us up for is direct substitution. Is to look at a function. If we're trying to find the limit, we're just going to do stuff like this. Take c, put it into the function, and there's your limit. Okay. Showing us that there's quite a few instances where that happens. Here's another instance where that happens. The limit as x approaches c of some root, the nth root of c, or of x, my apologies, not of c. Okay, this is just some root. So wherever I go on this function, I go up to x. The way that I find out what the y value is I take the nth root of x, right? And that's going to be some set constant number, like we're going to be taking the third root of an x or the fourth root or so on. And it'll look something like this, right? Because I'm going to have a number and I'm going to take its root, so we're just going to get smaller and smaller and smaller numbers. So that's pretty straightforward, that whatever this root is, the third root or the fourth root or whatever, that's how I find these values. So if I want to know this limit at, if this is my c, limits to values on the left and the right are going to be approaching just the value of the function if I were to plug c directly in to the function. Okay, and of course the caveat is as long as this guy is odd, or if it's even, then it needs to be positive. It's not that spectacular condition, but there it is nonetheless. Right. Now, theorem 1.5, the limit as x approaches c of f of g of x. So remember, this is what we call a composition of functions. We say that this is f of the limit of, or as x approaches c of g of x. So that would be f of L, because let's say that say that if g of x, let's go up just a little bit, ignore this, if the limit as x approaches c of g of x is L. Okay, so here's what it's saying. If we're finding this limit and we have a composition of functions, then we could just kind of move the limit in here with g of x, and if we know this limit, we can take that limit. That limit's going to be a number. That number is just going to go into the function f, and we're going to find f of l, and that's going to be our new limit. Okay, so at this point the limit gets evaluated, and then the limit is not a consideration anymore because we've already found it for g. Okay, so if you know the limit for some function g that's inside another function, then you can just find that limit, put that number into f, and find the result. For example, just the example that follows, the limit as x approaches 0 of this function, x squared plus 4. Well, this is, let's see. Well, since I know that, I can find this limit, right? This is a polynomial function, so let's find this limit. This limit would be, put in a 0 for x, that's 0 squared, plus 4, that's going to be 4. Alright, and the limit as x approaches 4 of the square root of x, we would just put a 4 in there, right? We learned that about in theorem 1.4. I can just take 4 and put it in there. So the square root of 4, we're going to call 2. So now if we want to know the limit as x approaches 0 of the square root, okay, the square root is this function, the square root of something. Square root of, now instead of just x, we put in this function. That's a composition. That if this were f and this were g, this would be f of g. Now I know this limit as x approaches 0 of this function, so I could just put the limit in here. The limit as x approaches 0 of x squared plus 4. I know that this limit is 4, so that number just goes straight into f, this other function, and this is 2. Okay, that's all it's saying. And now theorem 1.6, I won't write them out, list them out, but we know that if we're familiar with a function and it's some curve, and we know that it is nice and curvy and it doesn't break up and there's no holes or anything like that, then at any point that I choose to find a limit, at this point C, if the function is defined here, if a y value exists, and we know it's all nice and connected, then what we call continuous, then we know that we could just plug in this value c into the function. That's what it's worth right there, and anything that we plug into the right or the left is definitely going to approach this value. So functions that are like that are all these trig functions, like the sine of x, and the cosine of x, and the secant of x, and the tangent of x. Okay, and we'll write out the rest. The cotangent of x and the cosecant of x. Okay, now let's see. These guys are good. These guys are nice, smooth, continuous curves everywhere. These kind of have a special condition on them that you have to watch out, because there are points at which we have things like vertical asymptotes and things like that. But if we're not at one of those points, we can just say, for instance, the limit as x approaches c of the tangent of x. Well, I can just put c in there, and there's the limit. Whatever the tangent of c is the limit, as long as we're not at one of those vertical asymptotes. Alright, so recall from class that we did something like f of x was equal to, I think, x squared minus 4 over x minus 2. And now what we did is we just threw it in our graphing calculators and found out that it pretty much just looked like this line. Didn't look curvy, anything like that at all. It looked fine when we looked at it. And then we plugged in 2. If you put in 2, the calculator would give you an error, and it should, because if I put a 2 into this function, 2 minus 2 is 0, and you can't have a 0 in the denominator. So that's where we would like to plug something in here, but we can't. We can't just say, alright, the limit as x approaches 2 of x squared minus 4 over x minus 2, and then just directly substituted it. That's what we're setting ourselves up, is to directly substitute. But we can't do that with this one. If we do, we're going to divide by 0 and we don't get a solution. Okay, but if we do this, now we make this x plus 2 times x minus 2 over x minus 2. Okay, now this function and this function are the same. What I'm about to do is to make them not the same. I want that to be clear, right? Because what I'm about to do is say these cancel out. Alright, and now I have this new function with this new limit of this new function. Okay, now understand, this is completely a different function. These two functions are different. They're not the same. It is true that everywhere else but 2, say you put in a 3. 3 minus 2 is 1, and 3 minus 2 is 1, so 1 is canceling 1. Put in a 4. 4 minus 2 is 2, and 4 minus 2 is 2. 2 and 2 cancel each other. Okay, they are getting canceled out everywhere except for at 2. Okay, or at least it appears that way. It appears they're eliminating each other, but they are a part of this function. But this function, it looks exactly like this function, except for at this little spot right here, right? Because this function right here, well, let's say this function, underline the actual function, has a hole right there. But this function doesn't. This function goes straight on through, no hole, and we're good. So at every other point but this one point, they agree. We say they agree. So then, if that's true, if they agree at every other point, then, you know, what if I put 2 into this function? Put 2 plus 2, that's 4. Well, that is the limit of this function up here. As x approaches 2, for this function, it approaches 4. So if we can invoke some kind of strategy to find another function that agrees, right? This function agrees at all points but C, and in this case it's 2, then we can just simplify this function to another function that agrees at all points but C, do direct substitution, and find the value of that function, and that'll be the limit of this guy. Okay, we'll do practice problems later. It should make a little more sense. And that strategy that will follow, finding those kinds of functions that agree at all points but one, we'll do that in another video.